Hello everyone. Welcome to this continued session on integration. We have stopped at a couple of methods of integration in our earlier session, wherein we have looked at doing the integration using the standard formulas, or doing an integration by splitting it into partial equations, or even doing the integration through substitution. There is one more method which we will discuss now, which is called as integration by parts, which is nothing but if you have, let's say, integration of u of x into v of x. So there are two different things which are multiplied together, dx. So whenever you have an integration in the uv form, u of x into v of x kind of a form, and I want to do an integration, one of the mechanisms that is suggested is you do it in parts. What you do there is, depending on what you choose as u of x and depending on what you choose as v of x, it comes out like this. First, you take u of x as it is and do the integration of v of x minus, what you do is integral of, take the derivative of u of x. This is the way. First you take u of x as it is, do the integration of v of x, and after that you take the whole integral wherein you take the derivative of u of x and multiply it with the integral of v of x. This is what we call it as the integration by parts. So this is also called as UV rule, wherein you integrate something which is of the form of UV in such a way that if you are able to integrate one of them but not the other directly, whichever the one you can able to integrate easily, you take it as V, and for whichever the one the differentiation can be done easily but not the integration, you take it as V and you use this kind of a mechanism. The better way to proceed is take the example like this. Now, integral of x log x dx. Now, if you try to see here, this is of the form u of x into v of x. But the difficulty here is I can't find the integral of log x. It's not that easy. Right? I can find the integral of x easily, but I cannot find the integral of log x. I don't have a standard formula to find the integral for log x, but I have the standard formula to find the integral of x. So what I'll do is I'll take log x to be u of x because I can find the derivative of log x very easily, and I take this to be v of x. The first step. Then you start with this u of x, which is log x, into integral of v of x. What is the integral of x? X squared by 2 minus integral of, do the derivative of log x, du by dx. I know the derivative of log x is 1 by x into integral of v of x, x squared by 2 dx. Now what is this coming out? X squared by 2 log x minus integral of, probably I'll take 1 by 2 out, and what is left is x dx. So again a simplification makes it x squared by 2 log x minus 1 by 2 into x is nothing but x squared by 2 plus c. So this happens to be the integral of x log x dx, or probably to be on the simplified side, if you still want to simplify it, take x squared by 2 out and you say log x minus 1 by 2 plus c. So especially when you have to do an integration of the form uv, where one of them can easily be integratable, whereas the other one is not that easy to be integratable. The one which can easily be integrable, you can take it as v, and the one which cannot be easily integrable, you take them as u. And after that, you can apply the formula as u of x into integral v of x minus integration of du by dx into integral of v of x. So if you remember this mechanism, anything which is of the form u of x into v of x, I'll again give you the form how you should remember it. If at all you have something of the form integral of uv dx, take it as u integral v dx minus, take it as integral du by dx. You have to differentiate u here and again take integral v dx. If you remember this mechanism, this is available even in the actuarial tables also. If you remember this mechanism, it can really help you out in trying to solve the numericals which are more specific to integration by parts. So all you need to remember is in which context you need to use this integration by parts. And as I clearly mentioned, if you have something of the form, or if you can express something of the form uv, where one of them is easily integratable whereas the other one is not, you can take the one which is easily integratable as v and the other one as u, and use this kind of a process to simplify it. I hope this mechanism is clear. Alright, then let's move on to the next one. If a particular integral, a definite integral, let's say it has to be differentiated. A derivative has to be taken on a definite integral. Let's see here, f of xt, which means there are two variables, x and t. So we are not talking about one variable scenario here. We are talking of two variables, f of x comma t, and the integration is with respect to t, not with respect to x. And the limits are in terms of x. Whenever you have such kind of scenario, and you have to find the derivative with respect to x. So these are the conditions. The integral is with respect to t, the limits are in terms of x, and the derivative is with respect to x. If that's the case, by doing this kind of a formula, you can directly do the differentiation of that. All you are doing is, with this example, it becomes much easier. So here if you see, this is my f of x. It is in the form of x as well as t. Two variables are there in it. The integration is with respect to dt, with respect to t. The limits are in the form of x, and the differentiation is being done with respect to x. So I can very well apply the Leibniz formula in this kind of scenario. What I'll do is, as a first step, take the limits, take each of the limits, find their derivatives, and substitute that limit in place of t. So what I am saying, what is the derivative of 2x plus 3? 2 into, take this f of x as it is, but wherever t is there, substitute 2x plus 3, which means x plus 1 whole squared plus 2x plus 3 into x. Am I right? minus derivative of 0, which is 0. 0 into this entire thing I don't need to really bother about. It's 0. So b dash of x, which is nothing but the derivative of the upper limit, take it f of x. But only thing is, instead of t, you place that upper limit value. Similarly, a dash of x, which is the derivative of the lower limit, into f of x by substituting that lower limit in place of t, plus again do the integral a of x 0 to 2x plus 3. Differentiate the f with respect to x, not with respect to t. So if I differentiate with respect to x, it becomes 2 into x plus 1 plus dx. If I differentiate with respect to x, it becomes t, do it as dt. Now what is coming? It's a matter of simplification now. X squared plus 2x plus 1 plus 2x squared plus 3x. And now come here. What is the integral of 2 into x plus 1 with respect to dt? In that case, 2 into x plus 1 is a constant. So it becomes 2 into x plus 1 t. Constant. For k, it is kt. And for t, the integration is t squared by 2. This you substitute 2x plus 3 and 0. So expansion is giving me 2x, so 3x squared. So this is becoming 6x squared plus 5x into 2, 10x plus 2. Here this is what is the scenario. Plus wherever t is there, I can substitute 2x plus 3. So 2 into x plus 1 into 2x plus 3 plus 2x plus 3 whole squared by 2. And when I substitute 0 in place of t, everything is 0. So I don't need to bother about that part. 6x squared plus 10x plus 2 plus, I can simplify this, right? 2 into 2x squared, which is becoming 4x squared plus 3x plus 2x, 5x plus into 2, 10x plus 3 into 2, 6 plus this is 4x squared. 4x squared by 2 making it 2x squared plus 4 into 3, 12x by 2 making it 6x plus 9 by 2. So on simplification, this is becoming 12x squared plus 26x plus 2 plus 6, 8 plus 9 by 2, 25 by 2 or something. So this is what is the derivative, especially using the Leibniz formula. Whenever I have to differentiate an integral, the integral is with respect to t. So these are 3-4 things which I need to be comfortable with, especially to apply the Leibniz formula. I need to express the function in terms of f of x comma t. The integration is with respect to one variable. Integration is with respect to dt. The limits are in terms of the other variable. Limits are in terms of x. Right? Even a constant I can mention it in terms of x. But the only problem is if I take a constant directly, the derivative of that constant is 0. So it really does not add any value. So only if it is in terms of the other variable, it makes sense to use. And the differentiation also in terms of the other variable x only. When this kind of a scenario is there, I can very well apply the Leibniz formula to do the differentiation of a definite integral. right? Is this mechanism comfortable? But yeah, if at all you are seeing a definite integral wherein there is an integration as well as a differentiation to be done. Integration is with respect to one variable, whereas differentiation is with respect to the other variable. Then probably you should start thinking whether the Leibniz formula can be applied, or can I transform the data in such a way that I can use the Leibniz formula to find the differentiation of the integral. Even that kind of thing you need to look at. Now, sometimes there could be questions which would be asked relating to convergence. In the definite integrals, till now, whatever we are looking at, you are seeing some definite integrals 0 to 5, 1 to 20. But there could be a possibility of 1 to infinite, like this example is asking. So I need to know whether the area between 1 to infinite converges to something, or does it diverge? Does it converge to something or does it diverge? How do I test it out? Very simple. Do the integration as if it's not infinite, it's some other value. Now if the question is integral 1 to infinite 1 by x squared dx, all I will do is I'll not do the integration as 1 to infinite, or probably I can do it, that doesn't matter, right? It's as good as saying, okay, let me do the integration for 1 by x squared. I can very well write this as x to the power of minus 2 dx. Now using our formula x to the power of n, x to the power of n plus 1 by n plus 1. So x to the power of minus 1 by minus 1 plus 1, or minus 2 plus 1, which is minus 1. Now you substitute infinite as well as 1, right? So minus 1 by x, I substitute infinite as well as 1. What is it giving? Minus 1 by infinity, minus of minus 1. So how much is it coming out to? Minus 1 by infinity will be 0 plus 1. So all it is saying is this particular value will converge to 1. So whenever the integral value is coming out to be a number which is not infinite or undefined, I say that the expression will converge. Otherwise, it will not converge or it will diverge. Now just imagine in this case itself, instead of 1 to infinite, if the question had been 0 to infinite, you just see here, minus 1 by infinite minus 1 by 0, so it is coming out to infinite almost. So it means 0 to infinite does not converge, but 1 to infinite 1 by x squared is going to converge. So what are we trying to say in terms of converging? If I try to find, convergence typically comes in only when we are looking at from an infinite perspective, and where one of the limits is infinite, and I want to see whether this entire integration comes out to one single value or it completely diverges, I can use this kind of a mechanism. Do the integration in the normal way itself, and what you can very well do is, if the final value comes out to be a finite number, you say that the limit is going to converge, the particular integration is going to converge, or it is otherwise it is not going to converge, it's going to diverge. So this is one more question that can typically come out as a part of our exam, so we need to be comfortable from that perspective also. Then the next aspect which we need to be comfortable with is the double integration. Till now we have been looking at integration only with respect to one variable, but it might be very much possible that a particular integration needs to be done with respect to two variables x and y. This is one of the scenarios which we come across in lot of our practical exercises, practical examples in the finance and mathematical world, wherein you may have to do the integration with respect to more than one variable. So here f of xy, I may have to integrate with respect to x as well as y. In those kind of scenarios, the logic is straightforward. You do the integration first with respect to one variable, either x or y, it's up to you. You do the integration first with respect to one variable, then with respect to the other variable. So when you are doing it with respect to x, y will be a constant. When you are doing with respect to y, x will be a constant. Straightforward. So don't look at it as any special case. You try to do the integration two times. One with respect to x treating y as constant. The next one with respect to y treating x as constant. That's it. Your double integral is done. So let's look at a couple of examples to get a hold on that process. Now, if I say integrate x equal to 10 to 15 and integral y equal to 0 to 5, 2x plus y by 3000 dy dx. Now, either I can start with respect to y or with respect to x. It really doesn't matter. Okay, so let's start with respect to y, which means x is treated as constant here. Okay, so I'll still say x equal to 10 to 15. So I'm doing it with respect to y. So the entire 2x by 3000, or probably I'll take the 3000 out to make things easier. So 2x is a constant here. So if I differentiate it with respect to y, it becomes 2xy. And plus y, if I differentiate it with respect to y, it becomes y squared by 2. I integrate it between 5 and 0. So what is it that is coming out? Integral 10 to 15. Substitute 5 in place of y and x, leave it as it is. So how much is that coming out to? 5, 10y, 10x plus 25 by 2 minus, if I substitute 0 in place of y, both of them are becoming 0. So this is what is being left with, and I am left with a dx. Now again integrate it this time with respect to x. Of course there is a 1 by 3000 which is outside, don't ignore that. So this 10x is becoming 10 into x squared by 2, and this 25 by 2 is becoming 25 by 2x. Again, this is between 15 and 10. So this part is nothing but 5x squared. 5 into 15 squared. 15 squared is 225. So 5 into 225 is 1125 plus 25 by 2 into 15, whatever it is, 375 by 2 minus 5 into 10 squared, 500 minus 25 by 2 into 10 minus 125, whatever it is. So this is coming out to 1125 minus 625, which is 500. 500 plus 375 by 2. So 1375 by 2 and into 1 by 3000. So this is what is the value of the definite integral, both double integration, because first we have done the integration with respect to y, then we have done the integration with respect to x. It really doesn't matter which one you are doing first. It just needs to be a logical workout. Now let's take one more example to get a clarity. So take this example here. So you can very well write this as x into e power 2x into e power 3y. So these are all x terms. So when you are differentiating them with respect to x, they are variables. This is a constant. And when you are differentiating with respect to y, this is a variable. This is a constant. That's the way it works out, right? All right. And now I need to do the integration like this. Okay, so first let me start doing the integration with respect to. So here, one of the intervals you could see that it is from y to 2. Y to 2 means this is definitely x is from y to 2 and the y is from 0 to 3. Right? Y is from 0 to 3 and x is from y to 2. So it's better to differentiate first with respect to x. So obviously if I have to differentiate it with respect to x, y will be treated as constant. So I am taking e power 3y as it is. Now how do I integrate with respect to x here? This is of the form uv for me. So I have to use integration by parts. So what I'll do is, I'll try to use this as u, this as v. Okay, u integral of v minus integral of x is, the differentiation of x is becoming 1 into integral of e power 2x by 2. So how much is this becoming? X into e power 2x by 2 minus 1 by 2 into, what is the integral of 2x? E power 2x by 2 again. This entire thing is integrated between 2 and y. So you can very well substitute e power 3y into, substitute 2 in place of x, you get e power 4 by 2. So I can take this out. 2 into e power 4 by 2, which is e power 4 minus 1 by 4 e power 4, right? Minus of, now you substitute y. Y into e power 2y by 2 minus 1 by 4 e power 2y. This is what is coming out. Now you simplify it, e power 3y into e power 4 minus 1 by 4 e power 4. These two are constants, right? E power 4 minus 1 by 4 e power 4, I can very well take it as a constant, minus y e power 2y by 2, or probably I can take e power 2y by 2 constant out, and it becomes y minus 1 by, or probably I'll take only y e power 2y, it becomes y by 2 minus 1 by 4. Now this entire thing is with respect to y. Now because this is a constant, I can ignore this constant and I can multiply it. What is coming out is either everything is in the form of e power y into e power some ky kind of form, or just e power ky. I can very well find out the integral of all of them, and that is how you simplify this kind of double integral. So first you do the integration with one of the variables, and then substitute the values correspondingly, and then take it up to do the integration with respect to the other variable. So as a concept you need to be clear with, if at all I am going to do a double integration, it has to be more like first do it with respect to one variable, assuming the other variable is a constant. Then you do it with the other variable, assuming the first variable to be a constant. This is what is the process when you are doing the double integration. The same concept can be extended to triple or n number of integrals also. Again, what we can do is this also integration using the numerical methods as well as working out on the differential equations. We'll take them out as a separate chapter, again as a separate session. So because this is a slightly lengthier session, I should say probably we can cut it off here in terms of uh, getting a good hold on. Probably you should do a practice first of all in terms of getting a hold on doing the integration by parts, and how do you do the Leibniz formula application, also looking at the convergence aspect in terms of integration, and finally how do you evaluate double integral. So these are all probably quite a new kind of topic. So if you have any further queries on them, you can give me a call on this number 9848012123. You can even drop in an email to me at vamsidhar@facegurus.com, and request you to visit my website www.facegurus.com to get further updates regarding the training and consulting activities in the areas of finance, investment, statistics, analytics, and actuarial sciences using tools like Excel, VBA, and SPSS. Thanks a lot for listening to this session. Thank you very much.